The opening thing to note is the daemon on my shirt, which is, someone asked me what's the oldest variant of the daemon, and the actual oldest variant of the daemon is actually on a Usenix shirt, which shows a PDP-11. But this was the first of the ones that John Lasseter drew. This was actually originally in black and white, and someone decided that it needed to be colorized. You know, how they take old movies and colorize them for the new. So at any rate, that's what this one is. And this is the one that appeared on the 4.2 BSD manual cover. And then the one that you've probably come to know better is the one that's on the 4.3, and then the running guy is the one that's on 4.4. All right, but that's not the purpose of this talk. Today what I want to talk about is superpages, in particular how they're used in FreeBSD. Now, we are actually quite fortunate that Alan Cox, who's the person that actually wrote the code and rarely travels due to the difficulty of doing that, is actually here at the conference. So if you want to like drill down and find out how it really works, he is the person that you should be talking to. Okay, that said, I'm going to start out with a little tutorial, a one-page tutorial, one-slide tutorial, on how memory management units work. Because if I start throwing around TLB and you have no idea what a memory management unit is, you'll be completely lost. So the basic game is that virtual addresses are being presented by the application, and the hardware somehow has to figure out where that actually lives in physical memory. And the role of doing that job is the MMU, Memory Management Unit. Now this is a very simplified version. I show what's called a single level page table here. And with a single level page table, the memory management unit takes this virtual address that's coming in, and assuming we have, let's say, 4K pages there, that means that the low 12 bits of the address are really just an offset into a page. So it takes the remaining bits to the left of those and uses that as an index into this page table. So the software sets up the page table, and it's got one entry for each page. So the 0th page there says, all right, if you get a virtual address that's somewhere in the first page, essentially, of the address space, then you come here, and it says, well, that virtual page actually lives over in this physical page in memory. And then we use the low bits to offset into there to actually get the data that you want out of that page. And now if you come along and you need something that's on the first page, then we index in there and we find out that it's in this other location. Okay, so what that really means is, since that page table lives in physical memory, is that every virtual address that you present actually requires two memory lookups. First, we have to look up in the page table to find out where the offset, or where the page is, and then we have to go get the actual data that you want. And it's worse than that, because if you think about big address spaces, you can't really just have a single linear array. So there's multiple levels of page. They call them page tables and segment tables and et cetera. And they can get like 4 or 5 levels deep. Okay, so in fact, you may have to do several levels of indirection through page tables before you finally find out where the page is that you want, where you can finally go get the data that you need. Well, that is a very time and intensive thing to do, because memory is really slow already, and to have to do multiple memory references for every for every address that's presented would absolutely clobber us. So in order to make this run faster, the memory management unit keeps something called a translation look-aside buffer, or often just called a TLB. And the idea of a TLB is to keep track of the things you've already looked up. So the first time you present something for page 0, it's going to actually go in that memory, it's going to get that answer, it's going to figure out where it is in the physical memory, and then it's going to go read that. So the first time you're going to pay those 2 memory references. But the TLB is going to keep track of that. It's going to say, okay, page 0, that lives over there. And the next time you present something that's on page 0, it comes in and goes, page 0, I know where that is, it's over there. And then we just skip doing the extra memory reference to get that information. And since you tend to have fairly localized accesses to memory, you keep hitting hopefully a small number of pages, and so after a few lookups into the page table, the TLB just knows what you're doing, and thereafter everything is just one memory reference per virtual address that's presented. Well, it requires a bit of work on the part of the operating system to keep that TLB up to date. So supposing that I go out there and I decide, well, you haven't used page 0 in a while, I'm going to take that away from you and use it for some other purpose. I take it away, I make an entry in the table that says it's not here right now. There's a flag word in there. But if I don't tell the memory management unit that I've done that, the TLB will continue to think it knows where page 0 is. So anytime I make a change in the page table, I have to notify the memory management unit. I do what's called a TLB shoot down. So I say, all right, page 0 changed. So if you know anything about page 0, just forget it. And now the next time a reference comes there, it'll actually go back and look. It'll see that it's not there. It'll generate a page fault. We'll go off and do the page fault handling, presumably give it page 0 back again, make another entry up there, shoot down the TLB again, and now it'll go through and it'll say, ah, yes, page 0, it's at this new location. Okay, so that's all well and good. The sort of fly in the ointment is every time we do a context switch, we completely change those page tables. We take away those page tables for the current process, and we put a new set of page tables for the one we're going to switch to, and now we have to do a TLB invalidate all. So just like forget everything you know, start over again. So one of the reasons that context switches are expensive is because we have to do this TLB sort of reset and start all over from scratch and rebuild it, what's in it. Okay, so with this in mind, we're going to start talking about TLBs and the problems that they bring to the situation here. What's the problem we're trying to deal with? Well, as machines have gotten bigger and processes have gotten bigger, the footprint that the process has gotten bigger, which is to say your working set. How many pages are you actively using at any point in time? And as your process gets bigger, your working set isn't as big as your virtual address space. Your working set is some subset of your address space. But nonetheless, the working sets have gotten larger. Well, typical hardware has on the order of 1,024 TLB entries. And the reason that it's that relatively small size, you say, well, why don't they just make it bigger? But the problem is that the TLB A has to be fast, and B has to be what we call associative memory. So when we go to the TLB and say, do you have this virtual address, it has to look at simultaneously all 1024 of its entries to decide if the one you're looking for is there. So we have to have 1,024 comparators all running in parallel in order to give us an answer. And there's a certain amount of fan out to run to that many comparators, so you have depths of circuitry, and the deeper the circuits are, the longer the delay through the circuit. And the whole point of this is to make this thing fast. I mean, if it's slower to go through the TLB than it is to read memory, we might as well just read the memory. So the upshot is that TLBs aren't getting bigger. They're getting a little bit bigger, but they're not getting very much bigger very quickly. So we're pretty much stuck with something on the order of 512 or 1024 TLB entries for the foreseeable future. So now let's go say we've got 4 kilobyte pages, and we can map 1024 of those. So if your working set is bigger than 4 megabytes, you don't fit in the TLB. That is, if you're touching more than 1,024 pages, then when you touch one that you haven't, that's not one of the 1024 that's in there, we kick out something that's in there and put this new one in at a cost of an extra memory reference. And now you go back and you're thrashing on the TLB. So your process, your working set, sort of everything runs fine until you cross that 4 megabyte, and then all of a sudden it just collapses in a greasy puddle. Okay, so how are we going to deal with this problem? We can't make the TLB bigger, or we can't. The hardware manufacturers aren't making it bigger. The page size is, maybe if we doubled the page size, we'd get to 8 megabytes, but that's still not really solving the problem for the size of programs that are being run today. So the solution to this is something called Superpages. Now, different hardware vendors have taken different approaches to it, but the general idea is to allow you to pick different hardware page sizes and to be able to do it not just on a per process basis, but actually within your address space to say, all right, this part of, this piece of it I'm using small pages, and this part I'm using bigger pages, and so on. Now, most of the hardware that's out there gives you a range of choices for the pages. So you can have your traditional 4K pages and maybe 64 and 256 and 1 megabyte and so on. But for the 386, Intel's wisdom, they decided that one superpage size would be sufficient. So if you're running on sort of the older processors that don't have the physical address extension, i.e. the ability to access more than 4 gigabytes of memory, physical memory, then you have a 4 megabyte superpage. So your choice is you can have a 4 kilobyte page or a 4 megabyte page. And if you're running on the newer processors that can access more than 4 gigabytes of physical memory, i.e. they have PAE, then it's a 2 megabyte is your alternate choice. Okay, so the address space can have a mix of regular and superpages. The addresses have to be aligned to page size boundaries. So if you've got 2 megabyte pages, then you've got 2 megabyte boundaries between pages, just as you do with regular size pages. And the payoff that we're getting here is that when you are using these larger pages, then for your 1024 TLB entries, you can now reference to gigabytes as opposed to 4 megabytes, or in the case of the 4 megabyte page, then you get 4 gigabytes. The point is that when we go to the super pages, we can avoid thrashing in the TLB. Okay, now it's important to keep in mind the problem that we are trying to avoid is thrashing the TLB. And the cost of thrashing the TLB is some extra memory references. When you start looking at the algorithms that we're going to use for deciding when to use super pages, they seem really conservative. But they're conservative relative to the fact that we want to avoid doing big memory-to-memory copies. We want to avoid doing extra I/O because it doesn't take very many extra memory-to-memory copies or extra I/O to completely wipe out any savings you're going to get from avoiding misses in the TLB. So you got to be very careful when you use super pages that you don't add other overhead. All right. So how do we decide that we're going to actually use super pages? Well, one of the things that you learn very early on as a developer of operating systems is that it cannot require the users to do something. The users can't say, oh, please use super pages from this application, because the fact of the matter is the users that should be doing it won't, and the ones that think that having super pages for LS is a good idea will be the ones that will set that request. So the point is that if at all possible, you want it to be something where you just analyze the applications, the processes that are running, and decide, this one, it looks like a sensible thing to be using super pages for, so let's go ahead and try and do that. Okay, so when you're running in FreeBSD, super pages is sort of happening, and if it's appropriate for your application to be using them, then they're going to get them. All right, so you may not say, why do I care? Well, you should still know what's going on. It's good for you. Okay, so how do we decide that we are going to use a super page? Well, as usual, we don't a priori really know exactly what your application is going to be doing, and so we need to sort of figure it out as we go along. So the first decision point comes when you map in the region and now you start taking a page fault. When you do the first page fault, we have to decide, all right, how are we going to service this? One choice is we can give you a 4K page. The other choice is we could give you a super page. Well, we don't really know necessarily what you're going to do, but we get some hints. So the first thing that we'll do is we'll say, all right, well, what exactly, what is this piece of your program doing? And when I say piece of the program, what I really mean is your program is made up of a bunch of objects. So one object is the text of your program. Another object is the initialized data of your program. Another one is the uninitialized data and heap for your program. Another one is the stack for your program. There's all these other things like loadable libraries and files that you may map in and so on. So we're making a decision on each object, on the first fault for each object within your program. Okay, anonymous memory is something like your stack or your heap or something of that ilk. And anonymous memory may be small when we first look at it. So for example, your stack is probably not very big, and it may be that when you do a subroutine call that you're going to then allocate the array of 1 million double precision floating point numbers and suddenly need 8 megabytes of memory. So for anonymous memory, we'll say, okay, we'll consider that you're a candidate for a superpage. The other thing is if you map a file in. Well, we look at the file. Files don't tend to change much in size, particularly once they've been mapped into memory. And so we just look at the size of the thing the file you've mapped into memory and say, all right, how big is this? Is your text the size of a superpage? If it is, then it's a potential candidate for a superpage. On the other hand, if it's the thing you've mapped in is less than the size of a superpage, it's unlikely that it's ever going to be big enough to qualify for a superpage. All right. Now, just because we decide that you are a potential candidate for a superpage doesn't mean we just immediately give it to you. First of all, there's a limited number of these in the system. And secondly, we need to see that that's something you're really going to do. So what we do instead is we give you what we call a Superpage Reservation. We say, all right, looks like your stack here is a candidate potentially for a superpage. So we're going to give you a reservation. We've got this superpage over here, but what we're going to do is just give you the actual 4K page out of that superpage that is wherever it is that you faulted. And then one of the other things we're going to do is we're going to look and see how that object is aligned in your virtual memory relative to this superpage. So people don't conveniently always map everything right on superpage boundaries. It might be that we're mapping this particular file in, and there's sort of half a superpage worth of stuff, and then there's several potential superpages that follow it. And so the offset to the beginning of the first superpage in that object may not be 0. It may be some amount. We refer to that as its color, not to be confused with the previous coloring stuff that we had in earlier versions of FreeBSD. And the reason that this is important is if somebody else maps, some other application maps that same file, we want to set it up with the same alignment, because if they align in their virtual address space differently, then we're not going to be able to share the superpages between them. And if, potentially we would have to do copying to get the necessary alignment, and copying is an absolute no-no. You copy 2 megabytes or 4 megabytes, you wiped out an awful lot of TLB misses. So we're just going to make sure we don't do that. On the initial alignment, we note the coloring. Now, if someone else comes and wants to map that file, we use this color to decide how to lay that out in their address space, assuming they give us the choice, which they usually do. Most people, when they do a PMAP, they just put it, I don't care where you put it, just put it somewhere in my address space. We'll say, okay, well, someone else already has it with this alignment. We're going to drop it in your address space with the same alignment so that if it gets promoted to superpages, we'll be able to share them. Okay, and then for each superpage, we have what we call a population map, which is to keep track of how much of that superpage you actually have faulted in. So sort of the summary here is we look at it, we say, all right, looks like this is something that could potentially use a superpage, and so we're going to reserve a superpage for you, but we're only going to give you the one 4K page that you need. And then as you continue faulting into that object, we keep track of how much of the superpage you have actually mapped in. So the superpage goes fault, 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 and it's mapping in page by page, 4K by 4K by 4K page, the various bits and pieces of that superpage. So now, at some point, we want to promote that superpage, because it doesn't do us any good if we don't ever actually get to use the superpage as a superpage. So what we do is we wait until you have individually faulted every small page of the superpage into your address space. And now we say, okay, you're clearly using the whole superpage. We've faulted it in, and we've been carefully making sure that all those pages are physically contiguous in memory, as they need to be a superpage. Now we can promote that superpage for your use. Now, the question is, do we promote it as a read-only page, or do we promote it as a writable page? Well, when you have each of those little individual pages, each one of the page table entries has a modify bit associated with it, so we can tell whether or not you've made any changes on that small page. Well, once we promote it to a superpage, we get 1 bit for the entire superpage. So all we know is somewhere within that 2 megabytes, you wrote a byte or so. And what that means is that if we promoted it read-write, and then you only wrote, you did sort of a worst-case scenario. You had 10 superpages, and you wrote 1 byte in each of the 10 superpages, and now we needed to flush it. We'd have to write all of that data out to disk because we wouldn't know where the 10 small pages were that you'd made that modification to. And see my earlier comment, writing all that out to disk just completely wiped out anything that we saved from TLB misses. So when we do the promotion, unless you've modified every single one of those small 4K pages within your superpage, we promote it to read-only. And so now you have the superpage, it's read-only. If you then touch it again, then we put you back to small pages until you go through and modify every page in it. Once you've done that, then we say, okay, fine. You're clearly modifying, a lot of stuff in here. Therefore, we're willing to promote it, even though we lose the fact of, exactly where you're doing it. This actually works better than you might initially think, because what typically happens is a superpage is either something like, the text. And those of you that run Emacs, that takes 50 superpages just to get the executable into memory. You're not modifying that because you're not generally setting breakpoints or doing other weird stuff like that in it. And so a read-only superpage is ideal for you. Or you're something like matrix multiplication thingy, and so you just go in and you're constantly, you walk, and you're just modifying everything all over the place, in which case a read-write superpage is, again, a sensible thing to have here. Okay. Again, the key takeaway here is that we cannot be having to write the entire superpage just because something tiny has been changed on it. All right. So we've got this. We've figured out how we're going to reserve the superpages. We've figured out how to promote them to be superpages. There's just one last little teeny-weeny problem that we have to deal with, and that is that a superpage, by definition, requires contiguous chunks of memory. And if we're in the mode of handing out 4K here and 4K there and 4K other places, then we pretty soon aren't going to have any contiguous chunks of memory anywhere. So how are we going to try and ensure that we have these big chunks of physical memory? And in order to do that, we need to have a way of continuously coalescing these pages as they come back to us so that we will be able to eventually put the little pieces back together and get the big pieces. This always appealed to me because I have the same problem with file systems. It's just not on quite the same speed with which you have to do it with paging. All right, as a side note here, the kernel is given superpages from the get-go, and that's what I mean by that is that when the kernel gets loaded into memory initially, all of the kernel's text, the initialized data area, the uninitialized data area are all dropped into superpage area. Thereafter, when it's running and allocating memory in its heap and so on, or loading kernel modules or whatever, it runs under the same schema that I've just been describing. But the initial kernel load just gets a superpage right away. Okay, that's why all of those of you that don't use those nasty loadable modules, you just compile the world's giant generic kernel. At least all your text is in a superpage instead of all these little pages. Okay, so historically, I was going to put in the thing that shows all the different kinds of ways that we manage pages, but I decided that was probably more than I had time to go through. So we have, let's just say, pages that are active in one way or another. They're either being used for paging or they're part of the so-called buffer cache, etc., or they were free. And we tried to keep the size of the free list fairly small. In preference, if there was extra memory lying around, we would let it be used by the file systems to keep the pages of recently accessed files around. Well, if you have only a small free list, it's very hard to get enough pages to coalesce them all together and get superpages. And so we sort of reorganized the way it was done. So now what we traditionally thought of as the cached pages, think of the pages of the file system that are lying around, we merged what was traditionally the free list and that cache list together. And between the two of those, we try and make sure that at least 5% of the physical memory is on one of those two lists. And in doing that, it allows us to coalesce them. So while we're coalescing these pages, they don't lose their identity. So if they've got file data on it, you can still get access to that file data. But once we pull one of these things together and we actually decide, all right, we're going to use it, then is when we go through and invalidate the cache entries so that so we can actually give it to you. All right, so we have these things called buddy lists, and buddy lists work sort of the way you would think. As pages come in, they get sort of, the pages that are next to each other end up together on the buddy lists, and so the buddy lists keep track of different things. So we have sort of sets of small numbers of pages, and then it's sort of by powers of 2. So we got 4 pages together and 8 pages together and 16 pages together and so on, and we sort of promote it up. And this actually works well, especially on the hardware where you can have multiple different superpage sizes, because that gives you better granularity in being able to go out and pick off a particular size that's sort of most appropriate for you. On things like the 386, it has to get all the way up to the sort of the biggest bucket size before we can actually use it. Okay, and so we have sort of 2 sets of these buddy lists. You can sort of think of it as one, which is what was sort of traditionally the free, and the other one, which was the cache. But even that's a bit on the muddled side. So if you just really think of it as a set of these things, and as the pages become available to us, we're aggregating them together. And then if somebody just needs a single page, we'll try and give them something that's not like the last page that would make up a super page. Rather, we'll give them something that is just sort of down in the rubble. So if you just always have the rubble pile and you need small pages, you pull it out of the rubble pile and you try and keep the things that are getting bigger together. All right, now at the moment, the page out daemon remains completely unchanged. So for those of you that have been through my lecture on how the page out daemon works, it's completely unaware of the fact that we're doing anything with superpages. It just decides, oh, this active should move to inactive, and this inactive should move to cache. And if we go to it and say, hey, we need some more stuff on the cache list, it just uses its usual algorithm to pull things off of inactive. It's not aware of the fact that certain pages might be more useful to us than others. And even just doing that, we still manage to aggregate superpages in fairly effective fashion. We could change the paging daemon to say, if you could just get me that page right there, that's the last coupon I need to put in my little book here to get a super page. But the problem is that page might be active, let's say. And so we have to take it away from that process, which would almost certainly fault it in. It would, of course, get a different page. But now we've paid a page out and a page in. And again, see earlier comments about what we're trying to save here. So instead, or if it was to pull a cache page out, we're going to lose the identity of a file page just to make a super page. And if someone reads that file again soon, again, we have to read it back in. So for all these reasons, although Alan tells me he actually did a little sort of prototype of modifying the page daemon slightly, a little bit leery about actually putting that in because it's not clear what the impact would be on the running system. So it should become evident now, as I've been going through here, how really conservative the whole thing is to avoid generating extra I/O or losing information that would cause us to have to do larger than expected I/Os or whatever, because even though the the gain that you get from Superpages is pretty dramatic, as you'll see on the next slide. Nonetheless, it's really easy to lose that, especially when you're in an environment where you're not in a constrained thing where you say, oh, well, I'm only going to use Superpages on things where I clearly know it's going to win. The upshot is that we could be more effective at coalescing these pages. It would give us the opportunity to have more Superpages, because what ends up happening is we can just have none. Something comes along that looks like it would be good for a Superpage reservation, but we can't really do it. We can actually revoke a Superpage reservation if you're not really showing that you're using it, and give it to someone else that looks more deserving. But modulo that, it would just be nice. If we had more Superpages, we could presumably do more good stuff. Okay, so what's the performance of this? There's a paper that appeared in the 5th Usenix OSDI, the Operating System Design and Implementation Conference. That was now, what, almost 10 years ago. If you really want to understand how the Superpages work, and particularly what the effect is of having a range of page sizes available, it's a nice light read. Well, it's interesting. Okay, so they ran a whole goggle of benchmarks, and I just picked and chose through them to give you some examples. So this is a set of some of the benchmarks. Then there's 2 columns here where it says the page sizes available. So these were the running time improvements that they got for machines that supported 8K, 64K, 512, and 4 megabyte pages. And then this is the same thing where the only Superpage size available was 4 megabytes. Okay, so as you can see, something like SpecInt, you get about an 11% running time improvement if you've got a range of pages, and what you'll typically see is about half that if you only have giant pages available. Some of them are really dramatic, like the matrix transposition, because it has a working set that is just sort of continuously going round and round. So without Superpages, you're essentially taking a TLB miss on every memory reference, and with them, you never take a TLB miss after the first time through. So it goes 6.5 times faster or something. And even with only the 4 megabyte available, it still gets a huge, huge thing. So you say, okay, fine, you've put up all the ones that look good. How about the ones that don't look good? Well, in the entire list, and there's probably 25 different things, there was one thing, SpecFloat 2000, that actually dropped in speed by 1.7%. And it's the only one where it was negative, and I won't say by a negligible amount. I mean, if that happens to be what you do for a living, you probably would be upset. But it was surprising to me that there weren't more things where one of those things that I talked about screwing up and slowing us down didn't actually kick in. So the fact that we were able to that it does as well as it does, I think, is a testament to just how well it's been thought out. Okay. I've already sort of talked on this, that the memory fragmentation can, in fact, reduce the number of Superpages available. In practice, when we actually run with it, we seem to get enough. I mean, the things that need them are actually able to get them, and when you do get them, when it's appropriate and you do get them, they work well for you. Okay, so with that, I will be happy to take questions. That's the link if you want to go grab the paper. So, yes?
How does the decision, or when does the decision?
So the decision on when to do the Superpage reservation is at the process is broken up into a bunch of pieces. So each one of those pieces, like the stack or the heap or whatever. On the first page fault that you take for each one of those, we make a decision as to whether or not we're going to consider you for we make the Superpage reservation, as we give you a small page, but from something that can be turned into a Superpage, if we think that you're appropriate. And that's either if you're a static file, you're big enough that you're going to cover a Superpage or more, or if you're like a heap or a stack or something, we just say yeah, because that could get big enough for that to happen. Yeah.
Can you comment on the hardware requirements to make more bits available for tracking which subsets of the
a lot of it depends on how they choose to implement the superpages. In the case of the 386 architecture, I showed just a one-level page table, but there's actually several levels. And so, the top level points to a set of points to a page that points to, each of which points to a page, which points to a set of pages. All they do is they remove that last level of indirection. So, what would be an entire page just turns into, one level higher. We just set a bit in it that says that, this is a super page. So there's not another level of indirection. You're pointing at it. And of course, there's only one bit in that entry. And so, if we were going to have extra bits, we'd have to find some place to put it. The hardware that's monitoring that is monitoring the thing that it points at. And so, at least in that architecture, I think it would be fairly difficult to come up with something like that. Now, some of the others, I haven't actually looked at the implementations of those. Alan could probably be in a much better position to answer, which of those might potentially be done in a way in which that would be sensible.
You mentioned that you don't give a super page until the user process has actually used every single page within that super page. Would it be beneficial to
The trade-off that you're making is that you potentially are, well, especially if it's a read-write page, you're losing, you're suddenly going to have to write that whole giant thing out. Another thing is that for whatever part of the page you haven't touched yet, we've got to initialize it. We have to zero it or read its contents in from somewhere or whatever. And that's a lot of extra work that you haven't really asked for. And again, the trade-off of I/O versus TLB misses, it takes a huge number of TLB misses before you pay the cost. And so by being as conservative as we are, we're really trying to mitigate those costs. Now, if the numbers that we were, that performance numbers that I showed you showed that we weren't getting any gain from it, that would give you more incentive to say, well, maybe we should be a little more aggressive about doing the promotion. But the fact of the matter is that under the algorithm that we're using, we're getting good gains on a wide variety of applications. Many, I was surprised actually, like the loader or something, linking the kernel. And we usually have relatively few negative effects. So my gut feeling is that we're in a pretty good position there. The other thing is, if you say, all right, when you get this close, we'd have to write code to go and figure out how to fill in the rest of the memory that we were about to promote and a bunch of other things. So it would be, it's not like a trivial, flip an if statement. There's more work than that that's involved. You follow up on that?
Yeah. Is there a fault with a reservation of superpages built in application? Suppose I have an application that's going to be using 1 megabyte.
There's a way you can tell the kernel that you're not quite using all of it, and that is to just read the rest of it and then ignore it after that. Because in some sense, at least by reading those pages, you're going to go through the normal fault in behavior and so on, and so you're going to do the work that we would otherwise have to do to fill that page out. I think more my answer to that really is we want it to just work behind your back. We don't want application developers to really have to think about it. And to the extent that they do think about it, if you know what the algorithm is and your application is such that, if we're using just a little bit more, well, then just go ahead and use a little bit more because then you know that it's going to get promoted. Yeah.
Also as a follow-up to that, I think I remember reading something about gigabyte superpages. This sort of have to fault everything in.
Under our current schema, yes, you would still have to touch all of it. But on the other hand, remember that you modify 1 byte somewhere in a gigabyte, we're up on the hook to write that entire thing out before we can free the page. So, in the back up there.
So I think I had 2 questions. You answered one of them already, which was more about the.
On the AMD, it's 2 megabyte pages and 1 gigabyte pages are the 2 choices. We do not currently support the 1 gigabyte pages yet. The AMD pretty much follows the 386 architecture, at a great distance with, make sure you don't have your reading glasses set too high. Okay.
There is any user-line tool to check if the application got assigned a Superpage?
There's a system called mncore, which is tells you, you point it and say, is this part of my address space in memory? And apparently there's some auxiliary information that comes back with that that says yes, and it's a superpage, presumably. Alan also thinks that there was some changes to Procstat so that you could perhaps get that information, but he says he's not sure if those ever got committed or not. But one could clearly think of a visualization tool. If the information's available, someone could make a little dancing thing that shows your address space with big pages and little pages. And little music would come out or something. Yeah. It's done exactly in the same way that the allocation would happen in user land. So even if you're doing small allocations, if your small allocations eventually end up to the point where you've done all of the pages of a super page, it'll be promoted to a super page. If the thing that you initially allocate is the size of a super page, since they're all going to be wired, it's going to more or less immediately give you a super page at that point. Yeah. Like many other subsystems in the kernel, there is a chunk which is machine independent, and then there's a machine dependent piece that has to be done. The only machine dependent pieces that presently exist in FreeBSD are for 386 and AMD. Then a discussion ensued, and Randall, who's been doing a bunch of work with the MIPS, said he looked at doing the machine dependent part and it looked like it was at most a few hundred lines of code. However, it must not have been a trivial few hundred lines of code because otherwise he would have simply done it.
Yeah, I did similar investigations years ago, weeks-ish with the work. For the to write this few hundred lines.
Yeah. It will clearly qualify for a Superpage reservation. When you do those little touches, if you're only touching, like, if out of every, let's say, megabyte, you're only touching one place in that megabyte, then that one page that you touch will get a single page, regular 4K page. The rest of it, assuming that you read it in or whatever, fault it in, whatever it is that you're doing, then it'll promote to a super page, but it'll promote to a read-only super page at that point. If you then modify it while it's a super page, we'll put it back to being individual pages until you show that you're really modifying sort of every page within that. So the answer is, the only time we're going to be having to write a super page size thing is if you've already shown that you've touched every page within it anyway, and so we're not going to be doing extra writing work.
So, as I understand it, when you walk the page table as part of the draw file, you realize that these pages run modified.
More modern tests have been run. The original tests were done on alpha, where TLB misses were essentially not entirely hardware, sort of microcode level stuff, so slower. But in the more modern systems, it really helps if your page tables are small enough that they fit in the L2 cache, because then you don't have to go all the way out to memory in order to get the answer. And so that's more of a win. And when you have super pages, you obviously have smaller page tables. Well, we've made it to 2:30. You all deserve a break. Thanks for coming, and enjoy the rest of the conference.